And that new approach came from a completely different mindset. Instead of an aggressive adversarial fight, this new idea was all about a slow, careful process of refinement. So let's welcome to the stage diffusion models.
This slide really just lays it all out, doesn't it? On one side, you have GANs, this all-or-nothing competitive game. On the other, diffusion, a patient, step-by-step process. And look at the results. Where GANs were unstable, diffusion is stable. Where GANs lacked diversity, diffusion delivers what we call high fidelity, just stunningly detailed and varied images.
I absolutely love this analogy because it makes the whole thing just click. A diffusion model doesn't try to paint a masterpiece from a blank canvas. No, it starts with a canvas full of random noise, pure static, like a block of marble. Then, guided by your text prompt, it carefully chips away at that noise, step by step, until a beautiful, clear image is revealed from within.
So, how does it learn to be such a good sculptor? Well, it's a really clever two-part process. First, during training, the AI learns by doing the opposite of what we want. It takes a perfect, clean image and, step by step, completely destroys it by adding noise until it's just static. This is the forward process. Then, it's trained to do the reverse process, to perfectly undo every single one of those destructive steps. By mastering how to reverse destruction, it learns the art of creation.
Now, this core idea was amazing, but the first versions were, let's just say, painfully slow. It took a couple more huge innovations to turn diffusion models from a cool academic project into the lightning-fast powerhouses we use today.
Two key breakthroughs really stand out. First was something called classifier-free guidance, which is a fancy way of saying they found a much smarter way to make sure the AI actually pays close attention to your text prompt. The second, and this was the true game changer, was latent diffusion. Instead of trying to sculpt a life-size marble statue, imagine sculpting a perfect, tiny miniature and then magically blowing it up to full size. The AI works on a much smaller, compressed version of the image, which is way, way faster. This is the secret sauce that makes models like Stable Diffusion possible.
And you can see the results right here in the data. Let's look at the FID score. Just think of it like a golf score for how realistic an image is. Lower is better. Look at Stable Diffusion and Imagine. They just crush the GANs. Then there's the clip score, which measures how well the image actually matches the text. Here, higher is better, and again, diffusion wins by a mile. But now look at that last column, inference time. This is where GANs still have a serious edge.
And this chart just hammers that point home. Diffusion models like Imogen give you absolutely incredible quality, but it comes at the cost of speed. A GAN, on the other hand, can spit out an image almost instantly. This fundamental trade-off between quality and speed is still one of the biggest research areas in AI today.
And that brings us to what's next. Because even with all this incredible progress, this story is far from over. Researchers are now setting their sights on a whole new set of challenges that are even harder to solve.
So what's on the horizon? Well, three big things. First, efficiency. The holy grail is making diffusion models just as fast as GANs, which would open them up for real-time uses. Second, understanding complexity. AIs still struggle with things like counting, a bowl with 3 apples, or spatial relationships, a red cube on top of a blue sphere. And finally, and this is a huge one, safety and bias. Making sure these incredibly powerful tools are fair, safe, and controllable is one of the most important challenges for the entire field.